So let's consider again the age that we found for the flat universe. Found that it was about 9 billion years. Well, evidence is indeed that the universe is flat. I don't tell you yet, but that's the evidence that we get from WMAP and from Planck. But there is something wrong with that, because you probably also heard that our best estimate for the age of the universe is of the order of 14 billion years. What's happening here is that this age we derived, if you remember, if you go back to the derivation, we assumed that the universe was filled only with matter. We made the approximation that the density was falling as 1 over a cube. This age is too low because this is an age of a universe filled with only matter. But there is more to the universe than just matter. Photons, for instance, outnumber baryons by 2 billion to 1. So let us include the effect of radiation in the Friedmann equation. For that, we're going to derive the pressure and the fluid equation. So let's go back to our expanding shell. We have considered only that the shell has kinetic energy and potential energy for the case of matter. But in the case of radiation, or other components of the universe, matter can produce pressure. To understand how this can be taken into account in cosmology, let us apply the first law of thermodynamics. So the variation in internal energy is equal to the variation in heat minus the work done. Well, if the universe has the same temperature all over, there is no heat flux. So you can set the Q equals 0. That is, the expansion is adiabatic. So the first law of thermodynamics becomes simply du is equal to minus dw. The variation is internal energy given only by the variation in the work. And the work is the PDV work. So P is the pressure and V is the volume. If you divide that by dt, then you have an evolution equation for the energy. And since the volume is equal to 4 pi over 3 times r cubed, then this equation becomes du dt is equal to minus 4 pi over 3 times the pressure times the derivative of r cubed. Now we can divide this energy by the volume and define the internal energy per unit volume, call it little u, then whose definition is going to be 3u over 4 pi r cubed. So the u is equal to 4/3 over 3 of r cubed times little u. If you substitute this u into this equation, then the factor of 4 pi over 3 cancels out, and you have d dt of r3 times u is equal to minus p times the derivative of dr cubed in time. Now, in the same way that you can write the energy as matter times the square of the sound speed, you can write the internal energy as the density times the square of the sound speed. So substitute the internal energy by this, and then you have ddt of rho times r cubed is equal to minus p over c squared dr cubed dt. Now finally, you substitute r by the scale factor, and you have r cubed on both sides, so the co-moving distance is canceled, and you write an equation in terms of the density and the scale factor and the pressure. Now this is known as the fluid equation. This equation can be used to determine the pressure of different components of the universe, or conversely, how rho changes in time.